This time I want to have a look at the other two cases of the first order response, those in which there is one zero but the zero is not at 0 Hz. And I'll use them as an example to show how the initial value theorem and the final value theorem can be used to simplify the derivation of the step response. First, however, I just want to note one thing about the results that we've derived previously. For the circuit where the input was going via a resistor into a capacitor to ground, the frequency response is 1 over 1 plus j omega RC, and as we've seen, the step response is 1 minus exp minus t over RC. For the other case we've looked at previously, where the components were the other way round, then the frequency response is j omega RC over 1 plus j omega RC. And the step response is just x of minus t over RC in this case. This first circuit has an initial value of 0, which we can either derive from noting that the voltage across the capacitor must be 0 just after the step has arrived, because it was 0 just before the step had arrived, or we could look at the frequency response and substitute in omega equals infinity and note that 1 over infinity is 0. And the final value is going to be 1, which we can get from the frequency response by substituting in omega equals 0, or just looking at the circuit and realizing that eventually the capacitor is going to charge up and get the same value as the input here of 1. Similarly, for this circuit here, its initial value is equal to 1, which we can get by arguing that the voltage across the capacitor must be 0 just after the step, and if the voltage on this side is 1, then the voltage on this side must be 1 as well, just after the step. Looking at the frequency response, we could equally get that by substituting in omega equals infinity, and once omega gets very, very large, we can neglect the 1, and that just gives us j omega RC over j omega RC, which is 1. And its final value is 0, which we can get from the frequency response by substituting in omega equals 0. Now, you'll notice that in both cases, the denominator of the frequency response is the same, which means that they have exactly the same poles. They have quite different looking step responses. This one has a step response that starts at 0 and asymptotes up to a value of 1. This one has a step response that shoots up to 1 and then asymptotes back down to 0 again. Time. The time constant of this rise and the time constant of this fall are the same. They are given by the poles in this response, but the initial value and the final value are different. The only thing different in the frequency response are the zeros, the numerator, which leads to this result that it's the poles that tell you the time responses of the step response, but the zeros that give you information about the initial value and the final value, where the step response starts and stops. Now let's go on to have a look at one of these more complicated first order responses. Okay, let's have a look at this circuit. We've got an input here, which is going to be our step, going through a resistor, down through a capacitor, and a resistor to ground. And the output is taken there. We can analyze it using differential equations as before by letting the current through the network be I, and noting that applying Ohm's law to this resistor here would give us that A of t minus x of t, that's the voltage across this resistor, is equal to I times R. Now the voltage across this capacitor, I'll call that VC. That is related to the current using the capacitor equation I equals C dVC dt. And the voltage across this resistor here is going to be the same as the voltage across this resistor here. That's just going to be, if I call this point here Y of t is going to be I times R as well. dVC, I can note that Vc is now x of t minus y of t. So I could write this equation as I equals C dx dt minus C dy by dt. I want to eliminate I from these equations, so I'll note that from these two equations I can get the result that at minus xt is equal to y of t. So I have a of t minus x of t equals y of t. And from here I get I equals y of t over r. So y of t over r equals c dx dt minus c dy dt. And I can eliminate y of t between these two expressions and get a of t over r minus x of t over r equals c dx dt minus c dA dt plus c dx dt. Well, a of t is going to be just a constant value of 1 at all times of interest, so that just gives me 1 over r minus x of t over r equals that term and that term add up and give me 2c dx dt, and this term here is 0, because if a of t is a constant value of 1, then dA dt is 0. This gives me dt over 2rc equals dx dt over 1 minus x of t. And we've integrated this type of thing before, from 0 to t, from its initial value up to the value at any particular time of interest, x. But we need to know the initial value in order to do this integration. Now we can derive the initial value by looking back at the circuit and saying, just after the step has arrived, there will be no voltage across the capacitor. So effectively, we've just got a potential divider with two equal resistors. We'll have the same current flowing through both of them. That means x of t is going to be a half, halfway up. That is 0.5. So that gets us to minus t over 2rc equals the log of 1 minus x of t evaluated between 0.5 and x, which is the log of 1 minus x of t minus the log of 1 minus 0.5, which is 0.5 minus log of a half. The log of something minus the log of something else is the log of this divided by this, so I could just write this as the log of 1 minus x of t over a half. Take the antilog of both sides and rearrange, and I'd get x of t equals 1 minus a half of e to the power of minus t over 2rc. And that's my step response. But that's rather a long-winded, complicated way of getting to the result, especially since we have to stop and think quite carefully about our limits of integration. It's considerably easier to get this result if we use the initial and final value theorems instead. And that would work like this. First thing we do is calculate the frequency response. And we can just use the standard technique of a potential divider to do that. It would be 1 over j omega c plus r. That's the impedance between the output and ground here, a capacitor in series with a resistor, divided by the total impedance in the network, 1 over j omega c plus 2r. There are 2 r's in the network. Multiply up by j omega c to get this in terms of the ratio of 2 polynomials, and we'd get 1 plus j omega cr all over 1 plus 2 times j omega cr. The initial value, therefore, the value just after the step has arrived, is the value of the frequency response at infinite frequency. At infinite frequency, we would have 1 plus infinity times jcr over 1 plus 2 times infinity jcr. Well, in both the numerator and the denominator, these terms are going to be much, much bigger, in fact infinitely bigger than the 1, so we can neglect the 1. Everything else cancels, that just leaves us with a half. Our initial value is a half. That's what happens just after the step arrives. The final value is the value of the frequency response when omega equals 0. And when omega equals 0, we just end up with 1 plus 0 over 1 plus 0, which is 1. So we already know that our step response is going to start off at a value of t equals a half, and is going to end up at a value of 1. It's going to move between the initial value and the final value with a single time constant, because it's a first order response, and the time constant is given by the pole. The pole in this case is going to be at minus 1 over 2 CR, radians per second. And the relationship between the pole and the time constant is that the time constant is minus 1 over the pole in radians per second. So in this case here, our time constant is going to be 2CR. So using that general form of the formula that I introduced last time, I could write that the step response is the final value, in this case 1, minus the final value minus the initial value, in this case a half, times e to the power of minus t over the time constant, in this case 2CR. And that's the same result as we got last time, through what I hope you will agree is a much simpler method. Apply the initial value, the final value, work out the time constant because it's minus 1 over the pole, and then just apply the general formula. The step response is the final value minus the final value minus the initial value times e to the power of minus t over the time constant. A circuit which exhibits the other response, it has the zero's break frequency below the pole's break frequency, is this one, where there's a resistor in parallel with the capacitor in this part of the network. And you can do a similar analysis of this circuit and end up that the step response is a half, that's the final value, minus the final value minus the initial value is now minus a half, because the final value is a half, but the initial value is 1, times e to the power of, well, the pole is minus 2 over CR, so the time constant is now CR over 2. And they're both just applications of the first order formula, that it's the final value minus the final value minus the initial value times e to the power of minus t over the time constant. Okay, that's almost to the end of these step response videos. There's just one little complication that I need to introduce and sort out, and that will be the subject of the last video.